Swayam Prabha. Digital India. Educated India.
Welcome to the 26th lecture in Mechanics of Materials. The last lecture we saw how to compute the moment of inertia about an arbitrary oriented axis. In particular, we saw that if y and z axis lies in the plane of the cross section, then Iyy given by integral z square dAx, Izz given by integral y square dAx, Iyz given by integral yz dAx. We saw how to compute these moment of inertias, and then we said that since the sign of the cross moment of inertia Iyz flips sign when the coordinate system rotates by 90 degrees, there will exist a orientation wherein it will go to 0. Okay. And we define such a oriented axis wherein the cross moment of inertia is 0 as the principal axis for the cross section, similar to the principal plane, principal directions that we have for these stresses and strains. Okay. So, we saw that, and then we said in the last lecture that we were interested in looking at a beam subjected to loads in two directions. In particular, we will now analyze what happens when a beam is subjected to a loading along its principal direction. This is a rectangular cross section, and the y and z parallel to the sides is a principal axis for this cross section. So, we are interested in studying what happens when I apply a load like this. It bends in this manner, and similarly if I apply a load perpendicular to this in this direction, you can see that it is bending like this. So, we are interested in analyzing what will be the displacement field and what will be the stresses that will develop in this cross section due to loads applied both vertically and perpendicular to the plane of the beam, okay, cross section. Okay. So, we are interested in studying this displacement coupled with this displacement in this lecture. Okay. So, now what we are interested is in this scenario wherein the load is applied along the principal direction, both the principal axis u and v axis. Okay. Then we are interested in writing what will be the displacement field. The displacement field u would be, there will be a delta u as a function of x eu plus delta v function of x EV plus along the x direction there will be a displacement negative u minus u naught d delta u by dx plus v minus v naught d delta v by dx into Ex plus. Okay. Let us see how does this displacement field arise when you have bending due to loads applied both along both the principal axis. Okay. It comes from plane section remain plane hypothesis, the same hypothesis that we used when the beam was bending along one direction. Okay. So, now when the beam was bending along one direction, you add u given by minus y naught d delta y by dx Ex plus delta y as a function of x Ey, right, because what we said was if this is the neutral axis of the beam, it will deform into a shape something like this due to bending. Okay. Then a section which is perpendicular to the axis of the beam initially will remain perpendicular and will remain plane. Okay. So, basically what happens is the tangent line to this neutral axis and this makes 90 degrees. So, this vertical line which now when extended down sees a displacement which is given by this distance, and this distance was I will magnify this figure. So, basically you add the neutral axis initially like that, and then it deformed into something like this, and this straight line would have been a straight line like that, but it deformed into some line like this, such that it is perpendicular to the neutral axis at that point. So, it would have been something like that, okay, and we are interested now in finding what this displacement is. We are interested in finding this displacement. This displacement would be, if I assume small rotations, this distance times this angle theta, and that angle theta will be related to the slope of the tangent to the neutral axis at that location theta. This is nothing but d delta y by dx if this is delta y, that deflection is delta y, that will be d delta y by dx, and hence this will be y minus y naught d delta y by dx, right. Similarly, now what is happening is it is bending like this, but instead of delta y there is a delta v coming in there. So, you have u minus u naught d delta u by dx Ex plus delta u, which is a function of x Eu, because the cross sectional axis in the plane of the cross section is u and v, okay. And then what happens is this straight line again, now instead of bending in the plane of the board here, bends like this outside the plane of the whiteboard here, okay. Since it bends like that, that will result in a displacement field of delta v of x Ev, delta v of x Ev, okay. And this delta v, similar to the arguments that we used here, will produce a displacement in the x direction, which will be now instead of y it will be z in this case, in our case it will be v minus v naught into delta v by dx, okay. So, that will produce a displacement minus v minus v naught d delta v by dx. This entire thing is the x component of the displacement, okay. That is how we got that. The remaining steps are the same. Now, I want to find the displacement gradient h, which is gradient of u, which would be minus u minus u naught d square delta u by dx square plus v minus v naught d square delta v by dx square, okay. And then it is going to be minus d delta u by dx minus d delta v by dx. Here it is going to be d delta u by dx d delta v by dx 0 0 0 0, okay. That is the gradient of displacement field, okay. Now, I am interested in finding the strain, okay. So, basically now I am interested in finding the strain epsilon, which is 1 half h plus h transpose, that will give me, this will imply that epsilon xx strain alone is non-zero, which will be u minus u naught with a negative sign d square delta u by dx square plus v minus v naught d square delta v by dx square, okay. Now, I have to substitute this in the expression for the axial force, okay, net axial stress sigma xx. Now, from here I will get sigma xx as E times epsilon xx using a one dimensional constitutive relation. then I am interested in finding sigma xx d ax ax, that is the net axial force in the cross section. This we said is 0 for beam bending problems. Okay. So, this has to be 0. This will imply that integral E times u minus integral E minus u naught d square delta u by dx square plus v minus v naught d square delta v by dx square dAx has to be equal to 0. Okay. Now, what happens? I assume the beam is homogeneous. This will imply I can pull out the E d square delta u by dx square integral u minus u naught dAx ax plus negative sign I can leave it out because it is equal to 0 dAv dx square integral v minus v naught dAx ax has to be 0. Okay. Now, you have one equation, but you have two unknowns u naught and v naught, which you have to find from the one equation. What the argument we give here is each of these individual terms, this has to be 0 for that to hold and this has to be 0 for the above equation to hold, because delta u and delta v are independent. I can have delta u displacement, but no delta v displacement. I can have delta v displacement and no delta u displacement, and still this equation has to hold. Hence, you require the individual components of this additive equation to be 0, from where you get u naught as integral u dAx by integral dAx, and you get v naught as integral v dAx divided by integral dAx, where dAx here means du dv. I am integrating in the principal axis plane. Okay, du dv. Okay. So, basically now this is the expression for u naught and v naught. Okay. Next, the expression is next I have to find d square delta u by dx square. Next, I have to find d square delta u by dx square and d square delta v by dx square. That comes from the moment equations. Okay. The moment equations are, I have m v moment given by integral u minus u naught sigma xx dAx. This is similar to mz moment being given by integral y minus y naught sigma xx dAx ax, where I have replaced z with v and y with u. Okay. So, basically I change from xyz axis to xuv axis, hence this change. Okay. Now, then what will I get? I got sigma xx as this equation in here, epsilon xx substituted in here with Young's modulus gave me the sigma xx equation. So, I will substitute that equation back in here for sigma xx to get mv as integral u minus u naught square d square delta u by dx square times E. Again I assume the homogeneous cross section of the beam plus v minus v naught into u minus u naught d square delta v by dx square dAx ax. Okay. Now, we find that u naught and v naught are nothing but the center of the cross section. From the expression that we got here, we understand that u naught and v naught are the center of the cross section. So, if the origin of the coordinate system is oriented at the center of the cross section, u naught and v naught would be 0, and hence you this equation will simplify to mv would be E times I v v d square delta u by dx square plus E times I u v d square delta v by dx square, but this by our definition of u v axis is 0. Okay. Now, here I have used the fact that u naught v naught is equal to 0 because origin is at u naught v naught. Okay. And I have used the fact that and the beam is homogeneous. Okay. So, that is the first equation. The second equation similarly will be the moment for mu direction, which will be integral v minus v naught sigma xx dAx. Okay. So, this is similar to my moment, which is integral z minus z naught into sigma xx dAx Ax. Okay. Now, this moment is, if I substitute for sigma xx, I will get this as mu moment as integral E, again I assume the beam is homogeneous, Ax u minus u naught into v minus v naught d square delta u by dx square plus v minus v naught whole square d square delta v by dx square dAx. This will simplify to E times IUV is again 0. So, this will be IUU d square delta v by dx square. For sigma xx, there will be a negative sign in there because epsilon has a negative sign in there. Okay. So, this will be this. Okay. So, now from for same reasons as this, you got this equation, same reasons here. Okay. Now, you have E d square delta v by dx square equal to mv by IVV, and solving these equations E d square delta v by dx square equal to mu by IUU with a negative sign in. Okay. Substituting, now I know how mv and mu varies as a function of x. So, I use this equation to find delta u and delta v. Okay. Then I substitute this entire thing into the stress expression to get my sigma xx as mv by IVV to u minus u naught plus mu divided by IUU into v minus v naught, okay, will be the stress in the member. Okay.